Nature of sound. Again, for this topic, we will go to Phet Simulation. So again, the link I will provide in the description below, so you may visit this website and try for yourself. So now we will have, or we will going to discuss the nature of sound using the simulation. Let's see how it goes. So here we have the introduction to waves. We have water, sound, and light. But particularly for this topic, we're going to sound. Okay. So you have here a diaphragm, and you can see the top view or side view. Okay. And also we have here tape measure, timer, and oscillation or graph oscillation. But anyway, we're not going to use these tools. So you can have this a full wave or just a pulse. Okay, so if you choose this just one pulse, okay, you can see here like that. But if we choose this oscillating and continuously produce sound, okay. So you can see here waves, but if you choose these particles only, so that's how it looks like. And for what? This one. Okay, let's in slow motion. Okay, so sun is a longitudinal wave that is created by a vibrating object, such as a guitar string, the human vocal cords, or the diaphragm of a loudspeaker. Moreover, the sound can be created or transmitted only in a medium, such as a gas, liquid, or even solid. So, as we will see, the particles of the medium must be present for the disturbance of the wave to move from place to place. Sound cannot exist in a vacuum. So you can see here in our simulation that the sound energy influenced the movement of the particles in the air. To see so the sound waves are produced and why they are longitudinal, consider the vibrating diaphragm of the loudspeaker. So when the diaphragm moves outward, it compresses the air directly in front of it. This compression causes the air pressure to rise slightly. The region of increased pressure is called condensation. Now let's see here the graph. Okay, so again, um, the region increase in pressure is called condensation. So you can see here the white region on the sound wave is we will call condensation. So in terms of graph, this area, let's pause muna. The area, okay, let's pause. The area here above the reference line or the point of equilibrium is what we call condensation. Okay? And it travels away from the speaker at the speed of sound. So after producing a condensation, the diaphragm reverses its motion and moves inward. So the inward motion produces a region known as rarefaction. So the region below our equilibrium line is the rarefaction, where the air pressure is slightly less than the normal. So each cycle of a sound wave includes one condensation and one rarefaction. And the frequency is the number of cycles per second that passes by a given location. So a sound with a single frequency is called pure tone. Experiments have shown that a healthy young person hears all sound frequencies from approximately 20 to 20 kilohertz. The ability to hear the high frequency decreases with age. However, a normal middle-aged adult hears frequency only up to 12 to 14 kilohertz. Sound waves with frequency below 20 Hz are said to be infrasonic, while those with frequencies about 20 kilohertz are referred to as ultrasonic. Frequency is an objective property of a sound wave because frequency can be measured with an electronic frequency counter. The brain interprets the frequency detected by the ear primarily in terms of the subjective quality called pitch. A pure tone with a large high frequency is interpreted as a high-pitched sound, while a pure tone with a small low frequency is interpreted as a low-pitched sound. So the graph shows that the air pressure varies sinusoidally along the length of the tube, or along the length of the space. Okay. So the graph also shown the pressure amplitudes of the wave, which is the magnitude of the maximum change in pressure measured relative to the undisturbed or atmospheric pressure. Loudness is an attribute of sound that depends primarily on the amplitude of the wave. The larger the amplitude, the louder the sound. The pressure amplitude is an object property of the sound wave, since it can be measured. Loudness, on the other hand, is subjective. Each individual determines what's loud depending on the acuteness of his or her hearing. So sound travels through gases, liquids, and solids, and considerably different speed. Now going back to our presentation, so you can see here the table at which the speed of the sound as it travels a different medium. And also on how going to determine the speed of the sound if it travels in a real gas or in a liquid in a solid bars using these formulas. Sound intensity is defined as a sound power that passes perpendicularly through a surface divided by the area of the surface. The unit of sound intensity is watt per square meter. And given this formula, I is equal to P over A, where P is the sound power and A is the area. So sound waves carry energy that can be used to do work, like forcing the eardrum to vibrate. In an extreme case, such as a sonic bomb, the energy can be sufficient to cause damage to windows, buildings. And the amount of energy transported per second by a sound wave is called the power of the wave, and it's measured in joules per second, or watts. So let's try to solve this problem. In the figure, we have here a 12 times 10 raised to negative 15 watt of sound power passes perpendicularly through the surface labeled 1 and 2. So we have here two areas. So these surfaces have areas of 4 square meter and 12 square meter. Let's determine the sound intensity at each surface. So at surface 1, given the formula, sound intensity is equal to P power over area, being solved for the sound intensity by dividing 12 times 10 raised to 5, oh sorry, 15. 15 watts over 4 meters squared. So the intensity is equal to 3 times 10 raised to negative 15 watt per square meter. And the surface 2, the intensity is equal to 12 times 10 raised to negative 15 watts over 12 square meter. Therefore, we have 1 times 10 raised to negative 15 watt per square meter. So we can see here that the sound intensity is less at the more distant surface, where the same power passes through a tripled crater area. So the ear of a listener with its fixed area intercepts less power where the intensity or power per unit area is smaller. The listener 2 intercepts less of the sound power than listener 1. With less power striking the air, the sound is quieter. Quieter. Okay, so let's have your test your understanding by solving this problem. Okay, to proceed, we have this decibel. So decibel is a measurement unit used when comparing two sounds intensities. So intensity level beta is defined as follows. So here is the table for typical sound intensities, intensity levels relative to the threshold of hearing. Using the hearing of human as the base or where we're going to compare the intensity, so we can get the level intensity here. So intensity level 0 or 0 decibel doesn't mean it has no sound. Instead, it is equal to the reference sound intensity. So the decibel increases as the intensity of that sound increases with reference to our threshold hearing.